Okay, today we are going to start the next concept, internal fields or local fields. So generally in a given dielectric material, how many number of fields are acting inside the atom of a given dielectric material. So consider here, this is a dielectric material. In this dielectric material, consider an atom A. On this atom, how many number of fields are acting? So that is the Lorentz field or local field or internal field is defined as the total electric field which is acting on an atom which is inside the dielectric material. Okay, so here the local field or internal field in a dielectric is the time and the space and time average of the electric field intensity acting on a particular molecule inside the dielectric material. Of course, in other words, the field acting at the location of an atom is known as local field or internal field. So, how many number of fields are acting on an atom which is inside the dielectric material? So, the internal field or local field must be equal to the sum of the applied field, external applied field, electric field E bar plus the field produced at the location of the atom by the dipoles of all other atoms. Now here, this is the local field E bar, EL is equal to, or EI is equal to the applied field, external electric field E bar plus the field due to all other dipoles. That means here, so for this, consider an atom within the electric material, an atom A, so which is inside the electric material, because this electric material is placed between the plates of the capacitor. So with the help of this capacitor, we have to apply an external electric field. Now here, consider a dielectric be placed between the plates of the capacitor, and let there be an imaginary spherical cavity around the atom inside the electric material. Say in this, instead of this dielectric material, consider an atom on which how many number of electric fields are acting. So the total electric field which is acting on the atom which is inside the dielectric material is known as the local field or internal field. So this is equal to here, the internal field at the atom site A can be made up of 4 components, that is E1 bar, E2 bar, E3 bar and E4 bar. So coming to each one. The first one, the field E1 bar, intensity of electric field E1 bar. So E1 bar is field intensity at the atom A due to the charge density on the capacitor plates. That means E1 is the intensity of electric field which is due to the plates of the capacitor. Okay, so E1 bar is equal to D by epsilon naught. Here this is the plate, capacitor plate. So this is positive charge is given to this upper plate, and the negative charge is given to lower plate. So this capacitor produces the electric field. This electric field produced by the capacitor is E1 bar. So which is equal to D by epsilon naught. But we know that D is equal to epsilon naught E bar plus P bar. So substituting D value in this one, so E1 is equal to epsilon naught E bar plus P divided by epsilon naught. So E1 bar is equal to, so epsilon and epsilon cancel, E bar plus P by epsilon naught. So this is equation number 1. So coming to the second component, E2 bar, the electric field. So the first component E1 bar, that is the intensity of electric field due to capacitor which is acting on this atom A inside the electric material, and the second contribution of the electric field E2 bar, which is due to here, E2 is the field intensity at here due to the charge density induced on the 2 sides of the electric material. Say E2 is the intensity of electric field due to the dielectric material, because here this dielectric material gets polarized because it is placed in the external electric field of this capacitor, so that the dipoles are induced within this dielectric material, so it gets polarized. So this dielectric material again produces the electric field. Say it's the electric field is taken as here E2 bar. Say the electric field produced by this dielectric material is also acting on the atom. A. So that is given by here E2 bar is equal to minus P by epsilon naught, because minus sign indicates this electric field produced by the electric material is in opposite direction to the applied electric field, okay, due to this capacitor. So external electric field is E1 bar, okay, and the electric field okay, produced by this electric material is E2 bar, which is in opposite direction, so that which indicates this negative sign. So that is equation number 2. Yeah, coming to the third contribution, that is the electric field, electric field E3 bar. E3 is the field intensity at A, okay, at an atom A, due to the atoms contained in the cavity. That means inside here, this is atom A, around this atom, let us assume a spherical cavity. Within this spherical cavity, there exists another dipoles, the neighboring dipoles around this atom A. So the water here, the electric fields produced by the neighboring dipoles around this atom is given by E3 bar. Of course, here we are assuming for a cubic structure, E3 is equal to 0. That means the electric field produced by the neighboring dipoles on this atom A is E3 is equal to 0. And last one here, the fourth component, fourth contribution here, the electric field E4. So that is, this is due to the polarized charges on the surface of the spherical cavity. Because here we have to assume that this is atom. So around this atom, there is a spherical cavity. Let us assume a spherical cavity around this atom within the electric material. So the charges are produced on this spherical cavity. So the intensity of electric field due to charges on the spherical cavity is also acting on the atom A. So that component is nothing but E4 bar. So you have to calculate E4, because you have to assume a spherical cavity around this atom A instead of the electric material. On the spherical cavity here, these are the charges, because here the spherical cavity, so on the spherical cavity on the upper surface here, positive charges okay, accumulated here, because here it is very close to the negative edge of this electric material, this lower surface of this spherical cavity. So here we have to observe the negative charge is accumulated on the lower surface, because it is very close and near to this positive side of this electric material. So on the spherical cavity, so it has positive charge, okay, on the upper surface. On the lower surface of the spherical cavity, the negative charge is accumulated. So around this point, around this atom A, just you have to assume a spherical cavity. So inside the spherical cavity, the intensity of electric field E3 is taken as 0. Okay, that is the intensity of electric field due to the neighboring dipoles around this atom A, it is taken as E3. But on this spherical charge, we have to we consider here the positive charge and negative charge is produced here. Second, this is a spherical cavity around this atom A. A is an atom. Around this atom, so there exists here a spherical cavity. So this is a positive charge and this is a negative charge. From 0 to pi, it is a positive charge, and it is also, it has from the lower portion of the spherical cavity, it is a negative charge. So here, this atom, so consider here, this atom, here this is A is an atom. Around this atom, this is a spherical cavity. So the intensity of electric field due to charges on the spherical cavity is to be calculated. So here this atom at the spherical cavity is that is under the application of this electric field E bar. So that is here. E bar represents the electric field, external electric field, which is produced by the capacitor. So now here on this spherical cavity, here on the spherical cavity, so let us assume the intensity of electric field due to this spherical cavity, charges on the spherical cavity at a point A. So for this here, consider a small area. So this is spherical cavity. Okay, the total surface area. Of course, you have to calculate the total intensity of electric field due to entire spherical cavity. So for this, consider a small surface area dA. So on the spherical cavity, consider a small strip with the area dA. dA is a small surface area. So here, this is small surface area. So dA. So here dA is equal to 2 pi into PQ into QR. So this is 2 pi, because the area of this small surface area dA on this entire spherical cavity. So dA is a small surface area. So dA is equal to, this is a 2 pi r. Of course, it is a 2 pi r. into this is dr, of course here. So 2 pi r, here it is 2 pi, peak is nothing but here, this is 2 pi, this is and area of the dA is equal to, okay, the small, consider small strip on this spherical cavity of area dA, which is equal to 2 pi into say PQ into this is QR. So because 2 pi is here, peak 2 pi into PQ is nothing but here. So because in this triangle here, say APQ, say this angle is theta, this is R. So take the value of here, PQ is equal to R sine theta, and QR is nothing but here. Say this is the value of the here. This is QR is nothing but R d theta, because here AQR is a sector with angle d theta with radius R. So this arc length QR is nothing but R d theta. So QR value is nothing but R d theta. Now consider the small surface area, a strip of small surface area dA on this entire spherical cavity. So how much charge is okay existing on this small surface area of a strip dA? Okay, so now here dA is equal to 2 pi into peak is nothing but R sine theta, and QR is nothing but R d theta. So R into R, 2 pi R square sine theta d theta. The value of here, the surface area of the small strip dA. So the value of the dA on this spherical cavity, here dA value is nothing but 2 pi R squared sine theta into d theta, where dA is the surface area between angle theta and theta plus d theta. Actually angle theta angle, okay, so theta angle, theta plus d theta angle. So here this is a small surface area dA. Now you have to calculate how much amount of charge is existing on this small surface area dA. Of course here, say consider, yeah, the total charge present on the surface area dA is dq. Now say on this surface area dA, so dq charge is existing. That dq charge value is nothing but p cos theta into dA. Now here already we know that. So p cos that p is the polarization vector here. Yeah, coming to here, just I'm giving some explanation here. So dq is equal to p cos theta into dA. How it comes here? I'm using here. Yeah, draw. So already we know that the polarization vector P is equal to here. The polarization vector, we know that the polarization vector P bar is equal to, it can be written as P bar is equal to mu by, okay, mu by V, unit volume. Okay, already we know that the definition of the polarization vector P is equal to the number of dipoles existing per unit volume. But actually we know that mu is equal to, already the value of mu is equal to charge Q into the distance between the charges Q into R divided by. So here the volume is nothing but the surface here, we consider the small surface area dA into, okay, radius. So this is a volume. So R cancel. So P is equal to, now the small charge dq is equal to, so for the small charge dq is equal to, so P into, okay, P into dA. Now here the small charge dq is equal to P into dA. Of course here, not here we're considered not P, here it is a P cos theta, because here, because why you are taking the normal component of polarization. So on the surface here, P bar is acting, okay, the normal component of, we are taking P cos theta. So P cos theta into dA. Actually dq is equal to P dA, but we are taking P cos theta into dA. Okay, so already we know that the value of dA. So here for this here, yeah. So the value of dq here is equal to, dq is equal to P into dA, but here P is nothing but P cos theta, because here P cos theta, because here, yeah, consider this small strip. So the polarization vector is always from pointing here, it is in this direction. Of course, interest of electric field, otherwise I'm drawing another graph here. So here, this is the spherical cavity. So consider this is a strip actually. Consider this is a strip. This is a strip of area dA. So here, of course, okay, draw neatly. Yeah, yeah. Consider a spherical cavity here. So on this spherical cavity, consider a small strip. This is the small strip of area dA. Okay, so this dA, so here this is a radius r. Okay, this is r plus d theta. This is a PQ. Okay, yeah. So the area of this here is nothing but the area of this is nothing but dA actually. Okay, so here for this one here again I will draw here. Yeah, on this one consider this is a small strip. This is a small strip of area dA. Okay, now here this is dA. So on this one here we have to here the polarizing vector p bar is acting in this direction. P bar is acting. Okay, so it's a normal component, that is P cos theta. Here it is the P cos theta. This value is nothing but P cos theta, because this is here the value of the intensity of electric field E bar value and P bar both are acting. Okay, E bar value and P bar here this is P cos theta. This is the P cos theta value. So here interest of electric field direction and component P cos theta, that is normal component of PNCPS, that is P cos theta తీసుకుంటున్నాము. So here this is P cos theta value. So here for this reason, so we are consider only P cos theta. Okay, yeah. For this reason, we are consider here only P cos theta. This is P is acting this direction. Okay, normal to this direction. P cos theta is, this is horizontal component here. So that is P cos theta, which is in the direction of E bar. So this is P cos theta. That's we are taken P cos theta, not P here. P cos theta into dA. So dQ is equal to P cos theta into dA, or P cos theta here, that is. But the value of dA is nothing but the area of this small strip dA. So the area of this small strip dA is nothing but 2 pi r square sine theta d theta. So by substituting these two here, the value of dA is substituting in this equation. Now the amount of charge dQ which is existing on the small strip of area dA is given by dQ. అంటే dQ dA ఏరియా ఉన్నటువంటి dA ఏరియా మీద ఉన్నటువంటి స్మాల్ చార్జ్ వాల్యూ dQ వాల్యూ వచ్చేస్తుంది మనకి. సో dQ is nothing but the amount of charge, okay, which is existing on the area dA. dA area తెలుస్తుంది మనకి. So the surface area of the dA is equal to 2 pi r square sin theta d theta. dA అనేటటువంటి surface area which is here, this small surface area dA, which is a part of this entire spherical cavity. ఆ స్పెరికల్ క్యావిటీ మీద ఒక స్మాల్ సర్ఫేస్ ఏరియా డిఏ తీసుకున్నాము. ఆ స్మాల్ సర్ఫేస్ ఏరియా మీద ఎగ్జిస్ట్ అవుతున్నటువంటి చార్జ్ వాల్యూ క్యాల్కులేట్ చేసేసావు. dQ is the amount of charge which is existing on the small surface area dA of the spherical cavity. So that dQ values are nothing but 2 pi r square, because P cos theta is already known. P cos theta is the same here. The value of d is nothing but 2 pi r square, so 2 pi r square sin theta d theta. Now the value of dQ which is existing on the small surface area dA of the given spherical cavity is given by 2 pi r square P cos theta sin theta into d theta. Now coming to third point here. Now the amount of here, the amount of electric field here dE4 due to this area, okay, dA, because the charge existing on this area dA is nothing but dQ. A dA surface area మీద dQ charge ఉంది. ఆ dQ charge నుండి ఎంత ఫ్లక్స్, ఎంత ఎలక్ట్రిక్ ఫీల్డ్ వస్తుంది. సో దట్ ఈస్ ఇంట్రెస్ట్ ఆఫ్ ఎలక్ట్రిక్ ఫీల్డ్ dE4. because of the charge dq which is existing on the surface area dA. Suppose దీని మీద dA అనేటటువంటి చార్జ్ తీసుకుంటే ఇంట్రెస్ట్ ఆఫ్ ఎలక్ట్రిక్ ఫీల్డ్ ఆ సర్ఫేస్ ఏరియాకి నార్మల్ గా ఉంటుంది. ఈ నార్మల్ కాకుండా ప్యారల్ కాంపోనెంట్ తీసుకుంటాం. ఈ బార్కి ప్యారల్ కాంపోనెంట్ తీసుకుంటే సో దట్ ఈస్ dq, దట్ ఈస్ dE cos theta వస్తుంది. సో dE4 here, dE4 is equal to 1/4 epsilon naught dq by r square. So that is the when here theta is equal to 0 direction. Theta is equal to 0 direction లో అయితే సో dq by r square వస్తుంది. బట్ theta is equal to 0 direction కాకుండా ఇక్కడ ఏం తీసుకుంటున్నాము, సో ఇంట్రెస్ట్ ఆఫ్ ఎలక్ట్రిక్ ఫీల్డ్ డైరెక్షన్ తీసుకుంటున్నాం కాబట్టి సో dq cos theta వస్తుంది. ఆల్రెడీ ఈ నార్మల్ డైరెక్షన్ లో తీసుకుంటే dE4 వస్తుంది. ఈ dE4 కాకుండా దీని ఏం చేస్తున్నాను, హారిజాంటల్ కాంపోనెంట్ తీసుకున్నా, దట్ ఈస్ dE4 cos theta. సో dE4 తెలుసు. సో ద వాల్యూ ఆఫ్ dE4 is equal to 1/4 pi epsilon naught dq by r square. బట్ cos theta కాంపోనెంట్ వాల్యూ తీసుకుంటున్నాం ఇక్కడ ఈ సర్ఫేస్ నుంచి ఈ కాంపోనెంట్ వాల్యూ. సో కాంపోనెంట్ వాల్యూ తీసుకున్నాం కాబట్టి అదర్ దాన్ theta here, theta not equal to 0 కాబట్టి theta is equal to 0 డైరెక్షన్ లో dE4 వాల్యూ దిస్ ఇస్ నథింగ్ బట్ in other than theta not equal to 0 ఈ డైరెక్షన్ లో, దట్ ఈస్ theta and theta plus d theta డైరెక్షన్ లో ఒక స్మాల్ సర్ఫేస్ ఏరియా dA తీసుకున్నాం కాబట్టి ఈ డైరెక్షన్ లో సో dE4 వాల్యూ ఇస్ నథింగ్ బట్ 1/4 pi epsilon dq by r square into cos theta. dq cos theta తీసుకుంటాం because this is dE4 cos theta. ఈ డైరెక్షన్ లో dE4 cos theta. సో dE4 is equal to 1/4 pi epsilon naught dq cos theta by r square. అంటే ఇక్కడ cos theta, దీనికి మధ్య డిఫరెన్స్ cos theta వచ్చింది. అంటే ఈ హారిజాంటల్ కాంపోనెంట్ వాల్యూ తీసుకుంటున్నాం. ఓకే, నౌ dE4 is equal to ఇప్పుడు క్యాలిక్యులేట్ చేయండి 1/4 pi epsilon naught r square 1/4 pi epsilon naught r square into dq cos theta. Already we know that the value of dq here, it is the value of dq is nothing but 2 pi r square p cos theta sin theta d theta. That value of dq is substituting in this expression. So dE4 is equal to 1/4 pi epsilon naught dq cos theta by r square. So 1/4 pi epsilon naught r square into so cos theta అలా ఉంచేస్తాము. So the value of dq is nothing but this is in bracket 2 pi r square. Okay, bracket open 2 pi r square p cos theta sin theta d theta value is nothing but dq and cos theta is the same. Now this is equal to here p by 2 pi cancel. So r square cancel, p by 2 epsilon naught into cos square theta into cos theta cos square theta sin theta d theta. This is the value of dE4. So this is the value of dE4, the intensity of electric field dE4, that is due to charge dq on this small area element dA. dA అనే ఎలిమెంట్ అనే dA అనేటటువంటి ఏరియా మీద dq అనే ఛార్జ్ ఉంది. ఆ dq అనే ఛార్జ్ వల్ల వచ్చేటటువంటి ఇంటెన్సిటీ ఆఫ్ ఎలక్ట్రిక్ ఫీల్డ్ dE4 క్యాలిక్యులేట్ చేస్తాం. మరి ఇప్పుడు ఎంటైర్ స్పెరికల్ క్యావిటీ నుంచి ఎంత ఫీల్డ్ వస్తుంది అనేది కావాలంటే దీన్ని ఇంటిగ్రేట్ చేసుకుంటాం. సో dE4 ఇంటిగ్రేట్ చేసుకుంటాం. thus the total field E4 due to the charges on the surface of the entire spherical cavity. So that is integrating this dE4 within the limits 0 to pi. Here it is positive charge and negative charge ekkada తీసుకున్న 0 to pi relation ఉంది కాబట్టి so integrating this dE4 within the limits 0 to pi, you will get the entire electric field E4 due to charges on the spherical cavity which is acting okay at a point A. Okay, that is on the atom A. So here E4 is equal to integral 0 to pi dE4, but dE4 is nothing but p by 2 epsilon naught cos square theta sin theta d theta. Substitute చేసుకున్నాము. Now p by 2 epsilon it is okay, it is a okay, దీన్ని బయటికి ఎలిమినేట్ చేస్తే so integral 0 to pi cos square theta sin theta d theta by calculating this value. Okay, p by 2 epsilon naught is here, it is a common. Integrating here integral 0 to pi cos square theta d theta, cos square theta sin theta d theta value is calculating by putting x is equal to cos theta, dx is equal to minus sin theta d theta. So by calculating this integral value you will get to minus 2 by 3. Okay, because we know that here p by 2 epsilon naught, so negative sign వస్తుంది ఇక్కడ minus p by 2 epsilon naught into minus 2 by 3. So here 2 to cancel, finally you will get the intensity of electric field E4, that is due to the charges on the spherical cavity which is acting on the atom at A. So that is given by P by 3 epsilon naught. So this is the intensity of electric field due to the charges on the spherical cavity. So totally already we have calculated E1 bar, E2, E3 and E4. Now the sum of all these components are contributions which gives the local field, internal field. Now the internal field EI is equal to the intensity of electric field due to capacitor. E2 bar is the intensity of electric field due to the dielectric material. E3 is the intensity of electric field due to the neighboring dipoles within the spherical cavity. E4 bar is the intensity of electric field due to the charges on the spherical cavity. The value of E1 bar is nothing but E bar plus the P by epsilon naught. That is from equation number 1 here. Equation 1 gives the E1 value, that is E bar plus the P by epsilon naught. Equation 2 gives E2 is equal to minus P by epsilon naught here, minus P by epsilon naught, and E3 is nothing but 0, E4 is nothing but a P by 3 epsilon naught. So minus P by epsilon naught plus the P by epsilon naught cancel. So the value, the expression for internal field or Lorentz field or local field is given by EI is equal to E bar plus P by 3 epsilon naught. So this expression, this is the expression for internal field or local field of an atom with electric material. So because this expression is very important, it will be used in the class-ismosity relation also. Now coming to the next one, class-ismosity relation. This is a very important concept. Both internal field and class-ismosity relation, both are very important essay questions. Now coming to, this is also very simple derivation. So coming to the class-ismosity relation. So consider a dielectric material having a cubic structure and assume that ionic polarizability and orientation polarizability are 0. So alpha I, alpha O is equal to 0. Okay, because here consider the electric material having cubic structure. It has only electronic polarizability. So that we know that the definition for polarization vector P is equal to N into mu bar as nothing but N into alpha into E bar. So yeah, N into alpha into E bar. So that is E bar is nothing but local field or internal field EI. So P is equal to N alpha E, where alpha is nothing but electronic polarizability, EI is nothing but a local field or internal field, where mu is equal to alpha E into EI. Okay, now but we know that the internal field or local field EI value is already calculated here. EI is equal to E bar plus P by 3 epsilon naught. Now substituting the value of internal field in this expression, P is equal to N alpha E into EI bar. Now here B is equal to N alpha E into EI, but the value of local field or internal field EI is equal to E bar plus P by 3 epsilon naught. So that is a value of P is equal to the polarization vector P is equal to N alpha E into EI is nothing but this value. So here by multiplying this N alpha E, so N alpha E into E bar plus N alpha E into P by 3 epsilon naught. So here this term is here, okay, going to this one LH side. So by taking P is common in both terms. So here P minus, okay, N alpha E, this is positive term, it is going to here left hand side. So P minus N alpha E P by 3 epsilon, it is equal to N alpha E into E bar. Now by taking P is common in these two terms, here P into 1 minus N alpha E divided by 3 epsilon naught is equal to N alpha E into E bar. Now P is equal to, this term is multiplied by P, so it is going to here RH side. So P is equal to N alpha E E bar divided by 1 minus N alpha E by 3 epsilon naught. This is the expression, say that is, so this is equation number 1. But according to here, the definition of P, polarization vector, P is equal to epsilon naught into epsilon R minus 1 into E bar. We know that the polarization vector P is equal to epsilon naught, epsilon R minus 1 into E bar. This derivation is also given in your WhatsApp group. I have sent this value, okay, this derivation part in our WhatsApp group. Please see here. Okay, so this is the definition of P bar. So P bar is also written as this one. So epsilon naught into epsilon R minus 1 into E bar. From equation 1, already we know that P is equal to N alpha E bar by 1 minus N alpha E by 3 epsilon naught. This is equation number 1. And this is equation number 2. Both equations from equation 1 and 2. So N alpha E bar by 1 minus n alpha E by 3 epsilon naught is equal to epsilon naught E bar epsilon r minus 1. So by solving this one, so here n alpha 1 minus, so here 1 minus n alpha E by 3 epsilon naught. Okay, this term is taken towards here, right, RH side, and this term is coming to this side. N alpha E bar, n alpha E bar by epsilon naught E bar into epsilon r minus 1. So 1 minus this term. So 1 minus this negative term is also going to RH side. So 1 is equal to n alpha E. My negative term is going to here positive term. So n alpha E by 3 epsilon naught plus n alpha E by epsilon naught into E bar into epsilon r minus 1. In these two terms here, yeah, in these two terms, so here E bar is a cancel. So n alpha E by 3 epsilon naught plus n alpha E by epsilon naught into epsilon r minus 1, because E cancel. Okay, here. Now here 1 is equal to, so in these two terms, again, take the common term here, n alpha E by epsilon 3 epsilon naught is common. N alpha E by 3 epsilon naught is taken as a common term plus, okay, 1 plus here 3 by epsilon r minus 1, because here there is no, okay, term 3. So that's why 3 by, because 3 cancel here, 3 cancel, the same term will occur here. So 1 is equal to n alpha E by 3 epsilon naught is taken as a common term into, okay, into bracket open 1 plus 3 by epsilon r minus 1. So then epsilon, this value epsilon r minus 1 into 1 is nothing but epsilon r minus 1, okay. Of course, n alpha E by, n alpha E by 3 epsilon naught is equal to 1 divided by this term, 1 divided by this term. So n alpha E by 3 epsilon naught term alone just 1 divided by this term. So 1 divided by 1 plus 3 by epsilon r minus 1. By simplifying this one here, n alpha E by 3 epsilon is equal to, so epsilon r minus 1 into this one. Epsilon r minus 1 పైకి వెళ్తుంది. So epsilon r minus 1 into 1, epsilon r minus 1 plus 3, అంటే epsilon r plus 2 వస్తుంది కింద డినామినేటర్. న్యూమరేటర్ లో అయితే ఈ epsilon r minus 1 పైకి వెళ్ళిపోతుంది. సో epsilon r minus 1 టర్మ్ పైకి వెళ్తుంది కాబట్టి, సో న్యూమరేటర్ లో epsilon r minus 1 divided by, so this is ఇక్కడ మనకు తెలుసు 1 into epsilon r minus 1 plus 3, that is epsilon r plus 2. So therefore n alpha E by 3 epsilon naught is equal to epsilon r minus 1 divided by epsilon r plus 2. So this equation is known as class-osmoticity relation. Now here, this where n is the number of molecules per unit volume. So the above equation is known as class-osmoticity equation. Using this relation, one can determine the value of electronic polarizability alpha A, knowing the values of epsilon r of the medium. So because this alpha E, n is the number of dipoles or number of molecules per unit volume. So alpha E is nothing but epsilon is a common epsilon r value. If you know that the value of its delta constant epsilon r value, okay, if we know that epsilon r value, then you have to calculate electronic polarizability alpha E, because n alpha E by 3 epsilon naught is equal to epsilon r minus 1 divided by epsilon r plus 2. Using this relation, one can determine the value of alpha E, knowing the value of epsilon r of the medium. So along with the elemental dielectrics, this equation is more suitable for gases and then, okay, and then for the liquids here. For crystalline solids, the interaction of dipoles with each other produce polarization, so which are more complicated than those of our simple model, and this equation is not valid actually. Now this is about class-osmoticity relation and local field, internal field, local field. So these two questions, concepts are very important because these are two essay questions. Okay, coming to last one, the applications of the dielectric materials. So these are the applications, uses of dielectric materials and applications of dielectric materials. So in our next class, we will see the applications of dielectric materials. Okay.